My name's Adam Brazier. I'll be talking about software continuity in sort of academic research projects. I think if you want to ask questions during, then shorter questions I will be able to answer during the talk, and longer questions we can just put off until the end. And this talk is being recorded. So a quick deal on me. During my PhD, which is some sort of theoretical quantum physics, I wrote a lot of fairly standard grad student code in C++, which did not see any use after I graduated. And then I became a postdoc, and that's when I got into astronomy, managing astronomy data and processing. I worked for the astronomy department, and then the Arecibo radio telescope, and then the CCAT telescope. And all through, I was working with the CAC, but as a sort of external researcher. And then I joined the CAC in 2015. And I've worked on a lot of different sorts of research projects, many of which are long-term, but in all of which I've always tried to develop code which is sustainable, so it'll last much longer than its immediate usage. And so what this talk is going to be is a bunch of the lessons I have learned as I went through it, picking the most important ones. I could give a much longer series of talks about lessons I've learned and things that went right and things that didn't. But I'm going to focus mostly on the ones I think are most important. So the central question is, how can we make software which lasts for long enough? Okay, and then there are immediate questions about what does long enough mean? What does lasts mean? How much will this cost is obviously important. There's only finite money in the world. And when we fail, how and why do we fail? And something I'm going to return to again and again every few slides is that if we analyze how things went, good and bad, in a sort of careful and blame-free way, then we will get better. And a lot of this actually requires the benefit of experience. So my scope's going to be, well, research projects at very different scales of operation, from small, just a few people, to sort of rather large distributed teams. It's explicitly for scientific research, but I'm going to draw on and refer to industry practices because most software engineers in the world work in industry. And it's addressed to anyone basically who's involved in producing, using, or managing the production of or use of scientific software. What I'm not going to do is I'm not going to give a big description of particular coding methodologies, sort of Agile Scrum say. It would just take too long. And I'm not going to take positions on which languages, frameworks, sort of whether you should be using cloud or on-prem, because the best choices will vary across the scientific domains and the context you're in. So my basic approach is going to be to try and explain problems and potential solutions. And I will refer to real experiences of mine and perhaps things I've heard from other people of developing scientific software. And I'll give some examples, 3 examples at the end very quickly. There aren't really any hard and fast rules here. Everything's trade-offs. But it's good if you have things in your mind, then you can be intentional about the choices you make. Okay. And when we do that and then we analyze it afterwards, experience makes us better. It will be somewhat idiosyncratic. I'm going to have picked, I don't think anything I say will be controversial particularly, but I might pick different things as the most important things than other people might pick. So please bear that in mind. So in general, what we want, and these are sort of statements of the obvious here, is we want our software to do what it's supposed to do, be usable by everyone that wants to use it or that we want to use it, and then be maintainable, extensible, and stable. And by stable, I mean basically its behavior and performance is consistent over time. So these are goals. They're very hard to define with testable metrics, although you might be able to do it for stability. And they are enabled by good practices, but there's no magic solution. So if someone says doing this thing is easy, they're trying to sell you magic beans, in my experience. The first thing is we should decide what the software should do. And this seems like a statement of the obvious, but it's very easy not to decide what the software should actually do before you start coding. But that's haphazard. And the results are often like complex, difficult to use, difficult to maintain, difficult to extend. Nevertheless, it does happen. So first thing I'm going to talk about are requirements. So the requirements tell us what the software must do, right? And these are the non-negotiable things. If it doesn't do this, we have failed in the production of the software. And in order for that to be true, the requirements have to be written so that we can assess whether or not the requirements have been met. And that's actually not as simple as it sounds. Some people don't like any sort of textual writing out of requirements at any level, and they push the whole thing into software tests. I actually like them at the high level. At the lower level, I wouldn't be producing requirements documents for everything unless it was a very critical component. Then you design software that meets those requirements. There's two sorts of requirements. I'm not going to dwell on this, but if you read the literature, you'll see that functional requirements decide what the system does, and non-functional requirements, which I call design constraints, typically address things like performance and security and so on. And that may come down to design versus architecture, as I'll explain in a minute. Now, in order to do this assessment of whether or not the design meets the requirements and whether the final software meets the requirements, you have to have a record of the requirements and the design. And then you can check the design against the requirements and the implemented thing against the design against the requirements. So you can spend any amount of time and money you want generating requirements. You could spend all of your money on generating the perfect set of requirements. That wouldn't be a good idea. And in particular, prioritization is the name of the game when it comes to generating software with finite money and time. And so the requirements should really embody what is absolutely needed, what is non-negotiable, not what is nice to have. And then you have to decide how much effort to put in. So Rich Wolski is a professor at University of California, Santa Barbara, often says, I work with him in a number of projects, often says, don't boil the ocean. So don't boil the ocean. And a lot of this comes down to experience and judgment. So here's another quote I like, which came from a computer science student. So that days of coding can save hours of thinking. So there is an amount of effort that should be put into the before coding, in my opinion. Now, you can read many books on this. There's a stack of books on my desk at home. And when I showed that in a previous talk, someone said that it looked like the worst book club ever. And yeah, I share that sentiment. So the time it takes to write requirements is it's how long is a piece of string. It really depends on the context you're in. I've seen 5 to 20% of effort, of total integrated effort spent on the high level requirements. I've also seen none. The none tends not to work out quite so well, but in essence, every time we do it, we should look back and think, did we do the right amount? Did we do it right? Okay, and if we did, then we can try and continue that. If we didn't, then we can try to do better next time, but not overcorrect. So getting the requirements has a nice description, eliciting. As I said before, there are things you must have. You can use use cases to achieve them. That's a whole complicated other talk, and many people do not use those now. In Agile, you may have heard of user stories. Those sort of embody requirements, but they're not formally written out. As I said before, you've got to write them so that we can tell if they've been met, and that can actually be hard. You can't say like the software must be fast or performant or responsive or something like that. That's not actually testable. And we can, in principle, and we should often write tests from the requirements. And they're not the only tests we'll write, but certainly we want to be able to test that the requirements have been met. And if you do write them in text, which I tend to, the standard form for writing them is the X shall Y, like the database should store the header information listed below for each file. That's something that came from a project on which I worked. It can be an unnatural way to write and takes a bit of effort, but it does mean that they're easy to read, which is very important because we're trying to design to implement those requirements. All right, so these are my recommendations. These are my opinions. I think writing out the high-level requirements before designing is good. These are sort of system level or very large component level requirements, even if you don't use them at lower levels, and I typically don't personally. What's even more important, perhaps, well, you have to have requirements to pass around, but you absolutely should pass them around to the stakeholders. This is the best way to spot what is missing and wrong. And I also find that making a draft set and then passing it around, particularly when you're working with scientific researchers, is much better than saying, can you please write me a set of requirements and handing people a blank sheet of paper. So talk to them first, try and work out what the requirements are, generate the requirements, then hand them around. And at that point, people are actually pretty good at saying, well, this is not here, or this is not as important, or whatever. And that also helps you loosely prioritize the requirements in case you have to descope. Changing of requirements can be very, very expensive, but sometimes it's necessary. Sometimes it turns out to be very, very easy. But the unpredictability of the cost of changing requirements means that effort spent working out what the requirements are beforehand is a good thing to expend. Right, so you get your requirements, then you come up with a design. Now, quite often people talk about design versus architecture, and architecture achieves those non-functional requirements of design constraints, and design achieves the functional requirements. I'm not going to stress on that here. I'm just meaning design to include both. But if you have a bigger group where you have like an architect, a software architect, then that will be a decision made by that person. Now, you can do the design in lots and lots of ways. The success of the way you choose to do design will come down to many things, but two in particular. Like, it should be obvious to people how the design meets the requirements, and that it will, and also what you should do when you're building the system. Developers have to be able to look at the design and implement it. And if that's not obvious, then they're going to get it wrong. So they won't really be wrong. You will have been wrong. Now, I personally am a big enthusiast for diagrams. I'm not good at making diagrams. It takes me rather a lot of effort, but nevertheless, I still find it worthwhile. The goal of the diagrams is obviously, to make things easier. That's a fairly sort of apple pie type of statement. But there are lots and lots of formats for diagrams. And again, it has to meet those goals of, like, you can tell whether it meets the requirements and how can I develop against it. So you pick whatever's right for you, and that will be contextual and based on sort of general culture in your community. However, a given sort of diagram, you should be consistent in the format you use across different components. Okay, so if you decide you're going to pick diagram like I show for system overview, then it would be good if all of them look somewhat like that, because it makes it much easier to read them all. And you can reuse them after the fact in the documentation. I'm going to show you a couple of examples which I like. I'm not holding them up as like a flaming sword of truth. This is just what I found useful in some projects in which I work, two of which I'll be discussing at the very end. So here's a sort of system overview for the system we built for P-ALFA. This basically just tells you what the system components are and what their relationships are. It doesn't really tell you what they do, although you may be able to guess if they've been named properly. And they're also, again, we use this when we introduce people to the implemented system, when we onboard new people. This shows the sort of data elements, the data types we have, and then what happens to them. The arrows show what happens to them, and the boxes are the sort of data types. This is summarizing at a high level what the system actually does. And you could have much more detailed diagrams for each of those arrows, for example, because there's actually quite a lot of complexity hidden inside some of those arrows. And then lastly, component level diagrams. I'm originally a database guy when I got in this game. This is a relational database diagram. This is how I design databases. So I just give you as an example of what a component diagram might look like. This is how I designed it. I was then able to look at it and pass it around people. We were all able to judge whether it was right, because it showed the relationships between things and also showed what was in there. And in fact, the biggest use of this historically, because this database has been produced quite a long time ago, is that when people have to code against the database, this is almost all that they need to get started. And then they can actually look at the data that are actually stored. But this summarizes exactly the state of the system against which you're coding. Okay, so just for examples, there's a multitude of different diagrams you can use, but I'm just showing you three that I have found very useful of different types. Okay, so how much design is enough? Okay, so my general rule here, which I learned from working with engineers, is that good enough is good enough. I mean, mechanical engineers, people who build telescopes that will fall down if they don't do it right. Okay, and you get better at judging when good enough has been achieved. But I think it's important, again, because a lot of this is about intentionality. We'll get better if we have things in our mind, we make decisions, and then we can reanalyze those decisions. If we make decisions by omission, then the only thing we can say is we shouldn't have made a decision by omission. So in general, and it's another obvious sort of statement, the design should contain enough detail so that you can generate usable code. It's not always easy to judge, because there's always this pressure to get coding straight away, right? Because coding is the real work, and if we're not doing the coding, we're not doing real work. In general, I find that only the high-level requirements are needed before starting, and you don't want to get into this analysis paralysis where you spend your whole time generating requirements and none coding. You need to get stakeholder agreement, particularly from the science team, who may be less familiar with the process of generating requirements. And when you've done that, in terms of what you start coding on, I would start coding against the riskiest areas, the things which, if they don't work, a whole bunch of other stuff will have to change. So I would start prototyping that to begin with. So you may have designed something infeasible, but if you can prototype and test whether it's infeasible, then you can change your design without having to junk a whole bunch of code, or else try and adapt a whole bunch of written code by some sort of sunk cost fallacy into a new design. Now, so once you've done your design, we need to implement the code, right? And we want to implement sustainable code. We have a whole bunch of decisions I'm not going to go through here, but one thing that will be important when you decide to focus on how much effort to put into stuff like documentation and installability and continuous deployment and things like that, will be what are the usage patterns? Are you generating community code that people will download and run locally? Are you generating a reusable library against which people will build? Are you building a service? Okay, so I've done all these sorts of things, and being aware of which of those you're going to do will, to some extent, drive how you decide to divide up the effort. Okay, so most code in the world, by far, is written in industry. Okay, but in scientific research, we also rely on code that we've written or code that other people have written. Now, what we would like to do is we would like to use industry practices, just because there's more people. They're also very clever. They've generated useful tools and knowledge, and they also have common interests with us. They want usable, maintainable, extensible, stable code. They live or die in many cases by that. However, the industrial environment and the academic environment are very different in some respects. I'm going to talk about how they're different, because when we understand the differences, when we understand the two contexts, then that makes it much easier for us to judge whether we can just take stuff right over or whether we can adapt it to our context and how we should adapt it. So this is judgment-free. There's no complaining or whining here, but some of the differences that I think are important, and a lot of my friends, being in the sort of general line of the business time, a lot of my friends work in private industry, and we talk about this a lot. They're interested to see how things are done in scientific research computing, and I'm very interested to see how things are done in industry. So we have, in general, lots and lots of part-time programmers who have other things to do. That might be because they're grad students or they're postdocs or faculty, or it might be because, like CAC consultants, we work on multiple projects. We have many science experts writing software who aren't trained as software engineers, and that's not condemnatory at all. It's just that if everyone's been trained as a software engineer, there's a certain sort of lingua franca between them and more mutual understanding. And in our cases, people are moving from science quite often, as I did, into writing more and more software. And we have to absorb certain things that were not part of our professional training. Very different career paths, of course. Grad students may enter industry, or they may become postdocs. Postdocs may enter industry, or they may become permanent researchers or faculty. That's different to how it works in industry, where people, progress through technical roles and then may become management. We do have, I said there was going to be no whining or complaining, but we do have different funding models. And as I said at the bottom, we also have lower budgets, but that's just part of our ground truth. We also have, sort of budgetary stuff like facilities and administration, some of which gets we get infrastructure that we can use, which doesn't get directly billed to us because we already paid it out of the overhead. So, but that can affect things like whether you want to move to cloud versus owning your own capital equipment on premises. We have very widely distributed teams typically, and as the team gets bigger, essentially it almost invariably gets broader. I work with people from all over the world now. So I'm a veteran of sort of 2 a.m. telecoms last week. That's now more common in industry, actually, although perhaps not spread over as many time zones as us. And there are just different cultures and imperatives, and again, that's not a normative judgment. Things are just a bit different between the two workforces. However, some things from industry that I said we'd like to use, but things that have interested me particularly, are how they do cost estimation. No magic beans there, sadly. It's still very hard. How management of the effort is conducted, and as I've done more and more sort of project management and management in general of software operations, this has become very interesting to me. And things like personnel churn, for example. when we're talking about sustainable projects or long-term projects, it just becomes much more likely, and it's an inevitability in industry. It's baked into their cake. And I think a lot of people have heard about modern software development practices, and I say modern, I should have put it in scare quotes, because some of these things date back to the 1990s and have penetrated science research in many cases, but that growth of newer programming practices is still ongoing in the scientific research field, in my experience. And one of the key things that these various methodologies have, so I've listed two there, sort of Agile / the Scrum version of Agile and extreme programming, that like focus on quicker development with shorter development cycles. I'll talk a bit about that later on. Okay, but first of all, I'm going to talk about cost estimation. And the bad news is that it's still a hard problem. We have to do it in the CAC. Everyone has to do it essentially because there is only finite time. We get better at it with experience if we look back at our decisions and see whether they worked, and learn from the ones that worked and the ones that didn't work. I personally think one of the reasons to have requirements and a design is it does allow basic estimation, because you can break it up into blocks. And the way I do this is after talking with some of my friends who are managers in industry, I sort of estimate FTE effort for each of the components of work, and then I sort of sum it up and cost it. And if you're putting in a big proposal like I was involved in last year, we had to do a work breakdown structure, and you had to say how much effort is going towards each thing, then you definitely have to be doing this. Now, if you've prioritized, which I mentioned earlier on with the requirements, then if you have to descope, it allows descoping. Sometimes you do it at the beginning when you discover that what you want is going to cost 4 times what is available. Some happens as you monitor progress, or even as requirements, that their priorities may change. So it's worth keeping on top of that. I'll talk a bit more about descoping in a second. One thing that's important, but also hard to define, it's a bit like nailing jellos at the ceiling, is this idea of velocity or coding velocity. How fast can we move? And obviously that depends on how hard the tasks are, but then also how fast we code. And when I say code, I include all the other stuff we want to do, like testing and documentation and so on, and working within our software development methodology, shall we share expertise. One thing I will say though, and I think this is really, really important, unresolved blockers are really, really bad for coding velocity, and there's no upside to them. If someone's waiting for someone else to get something done, then they're either spinning their wheels, or they're working on some other project and may not be available when you need them, or they're just doing some lower priority thing within the same project. So resolving blockers is an absolute key element. I'll talk about a bit more when we talk about management. So when you have a feel for coding velocity, you can work out how long is it going to take, and you can also assign tractable things in given periods. And so when you split tasks into things that can be done in parallel that all have to be finished about the same time, it's pretty important that you have a good idea when they can be finished. And it'll also allow an early recognition of when timeline is under threat. We have an instinctive feel for it, but again, being intentional about it, thinking about it explicitly is very valuable. Now, in various things, in Agile Scrum, you might have coding points that measure your velocity. I'm not going to go into individual coding methodologies. So when you do it to descope, well, first of all, we don't want to overpromise, right? But we want to be ambitious. So that means we're always under timeline pressure. But one thing is that we can always, it's sustainable software, it's extensible. So some things that we descope essentially are just pushed out. We might have to ask for more funding, or we might do them if we have time. But it's not necessarily a disaster if we have a prioritization. Now, one thing that's absolutely true, it's been known for over 50 years. It's in a very, very, very good book on software development called The Mythical Man Month, which is older than me. You can't fix a timeline problem by adding more people, even if you have more people that you can afford, right? In practice and in general, you either have to extend the timeline or you have to reduce the scope. You have to descope. That's just how it goes. But it's not always a failure, because we're working in scientific research, and if these things were easy, they wouldn't be giving us research funding to do them. But we should gain experience from them so that we make a better guess as to how long things are going to take in the future. Right. Now, the next thing I was going to say, I was going to talk about from industry, but how we do it in our context, is management. So producing software is an effort that still involves human, and human efforts have to be coordinated. we need to give tractable work to the people doing the work, but all of these Legos, all these little blocks of work have to go together so that we move towards the construction of working software. Okay, they're not each mini research projects that might go anywhere. In the end, we have an overall direction in which we have to move. Now, lots of programmers will move on, particularly over longer term projects of the sort that characterize sustainable software. So it's important that the code doesn't die when this happens, which is exactly what happened with my grad student code. As soon as I moved out of theoretical quantum computing, I suspect that code was never used again. So it's hard to define what good management is, particularly in our context, okay? Because often it's defined in terms of counterfactuals, like, you know, the house didn't burn down, things didn't go wrong. Now in industry, they have the benefit often of many managers, and they can compare across them. Often we don't have any, right? So I'm talking about management, and this may be a shared responsibility amongst everyone rather than managers, because we may not have, in some projects at least, a dedicated manager. One thing we can do is we can compare the output to the requirements. Again, it's not a good reason to have requirements, because that's the job of the production of the software process that's run by management, is to produce software that meets the requirements. However, we should also evaluate the outcomes in general, right? And work out why things went well, why the things that didn't go well. And this has to be blame-free. I'll talk about this a bit later on, but people will not take part in a process where their first priority is to avoid getting the blame and suffering professional consequences. So personnel are, in the end, the most important thing, because they produce the code, and we need talented people. And we're fortunate, particularly given our lower budgets, at how many very, very talented people there are working on scientific research code, because it's cool. It's just great, and it's interesting, and a lot of people spend their whole careers in this. However, if you're, you know, in a big city, you may not be able to afford big city wages for coders, given what they might earn. Or if you're on a campus in a remote part of sort of rural part of the US, the pool of available people around you may not be big enough that you can always find someone. So you should be required to recruit remote talent, but that does require a certain amount of management in itself. Once you have one, it scales pretty well, but the difference between none and one is fairly large. Most of my work has been remote all the way through since 2005. Career progression is hard, because this is an institutional issue, and places like the CAC can have some career progression because there are a number of us. But smaller teams, it is pretty difficult. One thing, though, that everyone can do is they can allow time for and encourage the development of new skills. That's professional enhancement on the part of those people, and that's valuable to them. Now, it may mean that they may take their skills elsewhere, but you're the sort of person that allows people professional development, so it'll make it easier for you to hire other people. There will be this churn now, and it's inevitable, because grad students and postdocs are almost driven to move, but software professionals will sometimes as well. However, we should embrace this, because the people who fund us, the federal government, in the main, workforce training is one of the things we're supposed to do. And that's what we're doing. We're training people, and then they take their skills elsewhere, and we have to handle that process. But it's actually a benefit, and hopefully they'll be producing sustainable software somewhere else. Right. Now, one thing that's particularly dear to my heart, given that I'm a CAC consultant, and I worked with CAC consultants back from when I was a postdoc, is a mixed team of science domain experts and the software professionals can be enormously productive. And this is the CAC model, right? Because you get huge expertise, right, from both groups. If you can integrate the groups into one community, you get camaraderie and mutual respect, but you also get this contextual understanding that's absolutely essential. Right? When things go wrong in industry or in academic research software, it's typically because talented people have built the wrong thing, right? And there's no point for doing the wrong thing right. So understanding each other's context is absolutely critical. And then, you know, we do demonstrations of the software that's being developed and learn more about the science that it develops. And in general, I bolded and italics it because I think it's so important. People cannot build software for which they don't understand the purpose. That's true in industry and academia, but in many cases, it can be a potentially bigger problem in academic research because we're so specialized at the cutting edge of scientific research. So time has to be allocated to running a process that brings people on and gives them the knowledge they need. Now, a sort of hidden statement here all the way through is like, you know, we're talking about progress, but how do we measure it? And it's actually pretty hard. However, if you have a coding velocity sort of approach and coding points and so on, it's absolutely sort of baked into the cake. You get that for free at the cost of having to come up with all that. But if nothing else, looking at timelines is a good way. How are you progressing towards the final goal? That requires a good breakdown of tasks. It requires a timeline, something like the fearsome Gantt chart. And you also want some measures of quality, right? Tests, but those come from the requirements. So we have that as well. In the end, it's all about achieving requirements in the time available with the money available. And again, learning and improving from experience is absolutely our goal here. So if we are tracking progress, we can also use it to learn and improve. It's a good set of data that we can employ. Right. So the last thing I was talking about from the industry side of things that we might want to take or that adapt or that we have to do even if we don't take it from industry are sort of the actual business of coding. Now, the more modern practices, and I did remember to put modern in scare quotes here, are built on much smaller deliverables than like build me a system. If you have smaller tasks and short cycles, then you can fail fast, but you also fail small, which limits the cost of failure, particularly if you order things in the right way so that the things which, if they can't be done, will affect everything else downstream. They're tested first, and then you can re-engineer if they don't work and you haven't broken a whole bunch of other components of your software. So you identify like minimum viable products as well, and you iterate around them. What's absolutely essential, and I'm just totally convinced of this, every single experience I've had of working in scientific research software, is that regular short communications amongst the team are really important. You know, daily stand-up meetings, for example, when everyone's in the same office, that was the original model. And now this is achieved via things like Slack or Microsoft Teams. And again, continued learning from experience. That's baked in to a lot of these modern coding methodologies and shared expertise, like pair programming, for example, shares the expertise. Right. Now, of all the things I'm going to talk about, this is probably the thing about which people are least excited. With documentation, but I think it's absolutely critical, and I still don't do enough of it, even though I do a lot more than I used to, and the teams I'm in do a lot more than we used to. So there's a bunch of different sorts of documentation, but the most obvious rule I think that I've learned once I realized how important documentation was, and it becomes more important the longer term the project is and the more sustainability you need, is that you have to produce documentation as you go. Otherwise, it won't happen. You'll end up doing those things you pushed out when you descoped, or the coding will never be finished in an ongoing project. So if you don't produce documentation as you go, there won't be any documentation. But without documentation, software will become unusable. Right? No documentation means no sustainable software. I will die on this hill. So there has to be documentation. And so once I've convinced you of that, you then oh, I've gone the wrong way. You then have to start planning what you're going to do about documentation. So the first thing, which is nobody's excited about this, like pick a document management system, right? Different types of document. You know, you can use Google Docs for planning, you know, requirements and design and stuff, and you can use Read the Docs for developer documentation. They can have different systems, but if you don't pick the system, you get one pick for you, but you won't get one pick for you. You may get as many picked for you as you have people, or even more. And that becomes then very difficult for people to find documents they need. So this documentation discussion, no one wants to take part in it, but get buy-in for it, at least in the sense that people aren't saying, I will not use that document system, or I can't use that document system. If you're working with people in China, for example, you can't use Google Docs. And that would be a bad thing to find out too late. You have to make sure the documents are shared with the people who need them. They can't be like continually asking for permission to see documents they need. That's a blocker, basically, and it will become extremely annoying. And they may make do without seeing the document they needed to see. And then again, good enough is good enough, and the judgment of that comes from experience. All right, so change is a fact of life, and it's absolutely a fact of software. Change code should be tested before you let it out. I think that's clear. You shouldn't roll things out to users and then rely on them to tell you it's not working. My simple recommendations here is use versioning, which is now much more common in scientific software than it was. It's not yet universal or ubiquitous, but it is more common, and you can use, say, for example, Git. Tests so that code can get a once-over. I'm not talking specifically about how you will do the testing, but particularly if you're deploying a service to people, you should test it before it goes live. So quite often you'll deploy it next to the production version and just test it until you're confident, and you can switch over. And there is the CI/CD, continuous integration, continuous deployment. There's lots of tech for that, which you may want to look into, particularly if you're deploying services. And again, you judge how much effort is appropriate. Now, here's something that I've always had in the back of my head. But usability, we all know usability is important because we want people to use their code. But if code that people can use has more reason to live, there is no reason for unusable code to be sustained. In the case of locally run code that people download and install, and this also includes libraries, installation has to be simple and reliable. That's the absolute key. And therefore, you need to be test it, but also be responsive to users who have problems. And that way, you'll get a lot more goodwill, and that will make the project much more sustainable in that community. So essentially, those questions I asked earlier on about what is long enough and what does last actually mean, to some extent, the answers come from the users. It will be based on a whole bunch of things, including whether the code serves their needs and whether the code is good, but also how usable it is. Right. I'm just going to talk very briefly about this. This is one particular approach that improves code quality and also shares expertise. It's having other people look at the code. And there's various ways of doing it, like pair programming, for example. It comes baked into the cake. If you have open source code, you'll get attention from outside. Hopefully, you'll get development help in the ideal case, and certainly you can get questions and queries and sometimes complaints, bug fixes, bug reports, and sometimes bug fixes. And all of this, you get much more of it if the code is systematic and commented, so that people can actually look at it. They're not just saying, I can't make it work. For some critical code, like we're doing in NANOGrav now for some of our analysis code, we're actually doing a full code review, making sure it does exactly the sort of thing it does. We're actually running it against other existing analysis codes, profiling its performance, and also checking we get the right results. All of this takes time, improves sustainability, but again, it's all trade-offs. There's only finite time, so you can judge exactly how you want to do this. Right, so now what I'm going to do, just in 2 slides each, I'm going to talk about 3 examples at different scales. Just as examples of how I approach this process of planning and executing code, but then also how I approach the process of extracting lessons from projects. Now, each of these projects has lasted very long. 2 of them are still going. So I'm just talking about one project within the overall scientific project. There's thousands of hours of software effort in all of these things. So what I'm going to do is over 2 slides, for each, I'm going to describe the software team, the problems that had to be addressed, the key outcomes, how it went, and then the lessons learned, which is related obviously to how it went, but it's not the same. And if we do this, if we go through and evaluate success and failure for projects, and I'm not evaluating P-ALFA per se, I'm evaluating the particular sub-project in P-ALFA I'm talking about, then we'll get better. And I know for a fact that as I've gone through my career, starting in 2005 in scientific computing after my PhD, I've got better. And it's the same as teaching, right? You evaluate how it went, how you did, and then you work out how to bake in the good things and how to redress the things that weren't so good. Okay, so for P-ALFA, my first project started in 2005, ran until 2019. It was using data from the Arecibo Radio Telescope, and as you may know, that telescope collapsed after earthquakes and hurricanes in 2019. Otherwise, it would still be running. The software team essentially was a programmer, systems administrators that was overtrained at the CAC, because we were working with the CAC right back then, and then a science team, a rotating science team of about 10 people, which included grad students, postdocs, permanent researchers, and faculty. And that included the people who are writing the analysis code. So essentially what was happening was terabytes of data were being sent on disk from Puerto Rico to the CAC. That was unavoidable because at that time there was not broadband. sorry, there was not very good broadband that could transport terabytes of data off the island. But then those disks were being loaded to tape and then being sent to Canada for processing, where we had time on a supercomputer in Montreal. And then also eventually we sent it to Hanover, where it was being processed on people's smartphones with the Einstein at Home project. This was an organizational nightmare. Posting stuff abroad, there were customs, you would lose some disks, there'd be damage to disks. It was very high latency and it was very hard to track what was going on. So sometimes you'd be sending the same files. It was very difficult. So we needed a tracking and distribution pipeline. Gather requirements. Even early on, I realized that requirements were important. From a subset of the science team, the PI approved it. I thought it would take about 3 or 4 weeks. It took more than 4 months. So first big project. But the final code actually worked for 14 years until the RSC observatory collapsed. I would think, there was over 4 months of effort put in. I think the integrated effort afterwards to keep it running was less than 4 months, this actual subsystem. So that was pretty good. We transferred hundreds of thousands of files, processed them, totaling over 500 terabytes. So the requirements solicitation actually went well. I did not do any breakdown for tasks. Okay, it was just like one big block. However, it was much better to extend the timeline than to descope, because it was a very long-term project that there already wasn't an existing system. We were just sort of muddling on. So we just muddled on for a bit longer. I would have been able to tell, I don't think I could have made it faster that much, but I could have told the team that it was going to take longer had I done a proper breakdown. In particular, I did not evaluate the amount of time it would take me to learn new skills. And that always takes quite a bit of time, and it should be built in. And if I'd been doing sort of prototyping short development cycles, I could have been reporting to the science team more often, and it would have been much better in terms of how people thought it was going. But also I might have got helpful input from some of them, because I was passing a 100 megabyte log file. Some of those might have had some insight into how it was written, because they understood the actual backend that was writing it. Anyway, so onto the NANOGrav project, which is still ongoing. I've been on since about 2008. It started off with one programmer and systems administrators at the observatories, at the West Virginia University, and at the CAC. The science team started at 25. It's well over 100 now. And that includes people who've written a very large amount of sophisticated analysis code. And they have also embraced modern coding practices as we've gone on. The code has been rewritten and been refactored and is now very installable, very usable, very readable, extensible, and is being used by the broader worldwide community. But that's not the actual project I'm talking about here. The problem we had there, basically, we have terabytes and terabytes of data, which have very complicated analyses performed on them. And then we have all the data products from that, and then the analyses get changed. Very long time baselines, like decades long, still ongoing. So we need to provenance everything. We need to make sure we don't lose anything. So what we needed was a data management and processing system, which I designed. I gathered requirements from a specified group of the science team that were working with me. I attended all of the NANOGrav meetings. I was fully integrated into the team. Actually, I'm now actually on the NANOGrav management team, elected by the members. I'm on the author list, as I was with P-ALFA. Both NANOGrav and P-ALFA have been really good about realizing that the software effort is a long-term effort, and incorporating the software people, the cyber infrastructure, the systems administrators into the team. And there's respect for expertise on both sides. It's actually been really, really good. So what are the outcomes? Well, we're still going. We've got a 15-year data release coming up fairly soon. The maintenance of the simple has actually been system has been pretty simple. The extension has been driven by like changes in instrumentation or addition of science goals, which is fine. And the system, as designed based on a relational database, has actually been very extensible in that way. So the effort has not been ruinous to extend it. So what did I learn from here? Okay, so the way we worked, and it wasn't necessarily planned this way, but the way we worked with breaking up things and communicating very broadly made it available for people to dip into the team and duck out, including undergraduate students. We had a couple of excellent undergraduate students who really drove us a long way forward. We're fully integrated in the science team, even more than was the case in P-ALFA, and this has been absolutely critical. It's not the norm in astronomy. I would say, although it is in some big collaborations now, and it's been instrumental to, well, it's reduced churn enormously, but it's also been instrumental to producing good results because we're talking to each other all the time. We should have done even more documentation than we did, much more than I've done in P-ALFA, but I think we're now realizing that we need more because 15 years and going is a long time. Institutional memory becomes very vague. So everything needs to be written down at the time, and you'll thank yourself in the future. We did better at estimating smaller blocks and, of work, and also resolving blockers, and that particularly happened when we moved to Slack communications. I don't think it would be an exaggeration to say that using Slack in the way we do, which is semi-continuous, has increased our productivity by at least a factor of 2. It's just been astonishing, and particularly when we need to get things done pretty quickly because things are happening, we have been so very, very much more efficient than we were in the days of email. And then the last project I'm going to talk about, which I'm also still working on, is SCIMMA. This is a software team of 6 professional programmers, about 20 scientists, 20 plus scientists, been running since 2018 or 2019. Now here, we're using Agile Scrum methodology, and a number of our programmers were actually not from the science domains at all. And the ones that were from very different science domains in general. So we use Agile Scrum. We have a product owner and a Scrum lead. That's me in this case. I've also the overall tech lead, chief architect. Those of you familiar with Scrum, we have 2-week sprints. We have a daily asynchronous Slack stand-up, and we do the normal sort of ceremonies like sprint planning, sprint review, and retrospectives and so on. So the problem was that we wanted a reliable, asynchronous, low latency messaging for astrophysics. So for example, to give one example, a transient event might be detected by the LIGO-Virgo Kagra detector, which will be starting again soon for its 4th observing run. And they might see 2 neutron stars merging, they'll send an alert out, and then everyone who gets that alert can decide whether they want to point their telescope at it or whether they want to do analysis of it. Telescope times are expensive, so this is a decision that you want to make, but the value of it for many science cases is the quicker you get your telescope pointed in the right direction. But actually finding the right direction is hard. So there's a really high cost to us being down. If something really interesting happens when we're down, then people won't get the messages, and that science is all lost. And it might be a long time until that rare type of event happens again. And the other thing we realized very, very early on is that because a lot of astronomy data is proprietary, at least in the short term, until it's been analyzed by the team that took it, we needed a way of doing permissioning. But authentication and authorization had to be built in from the beginning. Right. So there had been a community consultation and a white paper generated from which SCIMMA emerged. And we all met for 2 days at a hotel in Chicago O'Hare Airport. And there was a huge amount of expertise in that room, sort of science domain side, people who were very interested as well in cyber infrastructure and cyber infrastructure professionals. We identified a high-level design then, and that's basically the essence of the high-level design we're still using, although the specific details have changed a lot. So in terms of outcomes, that system is actually now being used by LIGO-Virgo Kagra internally, and it's also being used for external messaging. And their 4th science run, 04, is imminent within weeks, and they will be using our system. So we're very happy that we have generated something robust enough for a billion-dollar project to use. For the external messaging, they've actually got a redundant system where they're posting to us and they're posting to the NASA tax system, which I think is also a really good approach as well, because we avoid a single point of failure there on the distribution to the community. The agile development method has worked in essence very, very well. We have adapted it somewhat, particularly as people have left or the sort of product cycle has changed. We've also integrated members of other teams, such as from LIGO and also from the Supernova early warning system into our Scrum workflow. And we actually wrote a paper with the SNEWS folk about doing this, about integrating with Scrum between the core team and the science team that we're using our service, and they're using it now. So in terms of lessons, I'd always known about the importance of identity and access management. You know, I've I've run proprietary systems, designed proprietary systems before for NANOGrav and P-ALFA, but the PI absolutely insisted it went in from the get-go. I had had a couple of experiences where it hadn't been in, and it had been a great deal of effort to retrofit it, and it was, in retrospect, absolutely 100% right. So I've learned a valuable lesson there, even relatively late on in my career. We built and maintained a client written in Python in this case that users can download as well to access our service. That was a really important decision, and it particularly enables participation from power users. But the friendly web interface, which was always in our roadmap, we should have put it earlier in the roadmap. It's basically done now. There's lots of beta testing and excitement about it, but it's called Hermes. We should have put that earlier. So that's another lesson I've learned, although, fortunately, no harm done, because we're going to be ready to go when LIGO 04 starts. The outreach to the broader community and user documentation takes a lot of time, but it's really, really important when you're serving a community of thousands, hundreds to thousands, depending on how things go. So I think we all sort of knew that, but it's become very obvious as we go how important it is and how much positive response when we do it. And when we give posters and demonstrations, we get lots and lots of positive response. So this is something that we're going to continue to do. So those are the three projects I was going to talk about. I'm just going to now make some observations, and then I'm going to give some conclusions. So some observations about these in all of them. So the scales are very different here, but what I've described in this lesson basically applied in different measures to all of these things. All of the projects actually worked. I've been fortunate, I think, that I haven't been on any failed project since that thing I did in my PhD that never turned into a paper. But all of them had lessons I've learned that have made me, and I think the others working with me, better as we go on to do more software development. The sustainability overhead actually grew with the project size, and that's not surprising because bigger projects, I think, they tend to require more sustainability in any case, right? Because there's more people interested in it. Quite often, the science goals remain valid for a very long time, but it's something that we did have to bear in mind. And the key ingredients that I would pull from what I've talked about that were also important for all three of these projects and many other projects on which I've worked were the importance of requirements, documentation, and sharing expertise between software engineers and scientists and within those sort of groups as well. Those have all been absolutely critical to the success, and where we didn't do as well, it's often because of deficiencies in those areas, which we remedied because we learn as we go. So last of all, my conclusions. So the results of producing sustainable code, almost by definition, are not immediate, right? Because you have to wait and see. But the payoff is great. And the way that we achieve this sustainable code is essentially by adopting the right basket of good practices, right? It's very difficult to pinpoint one exact thing you did that meant that this piece of code was in use 14 years later. It's a mix of things. And part of what you learn is also how you might have done it quicker and achieved the same sort of longevity and functional quality. But the payoff is really, really good when the codes are sustainable. Communication between the scientists and the coders is, I think, critical. I just don't see how it can work without it. And in longer term projects where the time commitment from the software engineers is sufficient to allow it, and also the available time for the researchers, having those groups combined is really, really valuable. So embedding within the science team is really important. And also creating an environment where people don't feel stupid asking questions. Because if people feel stupid asking questions, they won't ask questions. And then if it's a software engineer who feels stupid asking that question, they're going likely to build something that doesn't serve the purposes. So we have to respect both each other's expertise, and we also have to respect where there is less experience, but still the ability to understand and express it in a way that's understandable. And that goes both ways between the software engineers and the scientists. This is all built on good people on both sides. I'm talking about the software side primarily. So do take care of the people. Give them a chance to grow, make them feel welcome, and you know, these are relationships that can last a very, very long time. So treat them that way from the beginning. And the last point, because it's the point I've made again and again and again, is that if we take this seriously, if we're intentional about this, if we have these sorts of things I've been discussing in our minds towards the goal of producing good software that lasts a long time and that we can extend, then if we evaluate the outcomes in a blame-free environment, we will get better at it. Right? And that's the real goal. We will improve as we go forwards. We won't keep repeating the same mistakes. We will just produce better and better software and more science. And in the end, that's a good use of the money that's spent on doing it. So thank you very much.